Should pop up with a little message, hopefully. There we go. Marvellous, thank you. Okay, so this is our fourth, I believe, tech seminar now, or virtual seminar, as part of the range of virtual seminars that we're doing as part of the Yorkshire and Humber Institute of Technology. We are doing this in association with all of our partners, but the University of Hull have particularly taken a lead on this, so thank you very much for that. So our fourth one, which is on the future developments in renewable energy, and is going to be delivered by Professor James Gilbert. So thank you, James, for being press-ganged into this. And just to say that we are recording this session, so just to let everyone know, but we'll also be making it available on our YouTube channel, our YHIoT YouTube channel afterwards. Okay, I'll say no more and I'll hand over to James. Thank you.
Okay, I'll just go through the usual process of trying to make sure we can share things and see things. So let me just okay, so hopefully you can see my screen.
Yeah.
Yeah, great, thank you. And I'm very happy to make this informal, so if there are any questions that come along as we go along, please let me know. But I'll also allow a bit of time at the end for any questions that anyone might have. So thanks for the opportunity to talk today. So I've been at the university for a long time and done lots of different things, but the main thing I currently work on is offshore wind energy. So although I will talk about renewable energy in the round, the focus will be on offshore wind. And that's mainly around working with organisations like Siemens Gamesa and Ørsted, who are, as you'll probably be aware, very big players in this field. And so, you know, some of the work we're doing with them is really pushing the boundaries of what's happening in the technology. What I wanted to do was just very briefly, and I guess this will be very familiar to some of you, talk about why we need renewable energy in terms of net zero and climate change and so on. A quick overview of the options, because although there are lots of different options available in terms of renewable energy, they've each got their own characteristics. And you know, for the UK in particular, offshore wind, as again you'll be aware, is such a big deal that I'll then focus on that, but in the context of what the other options are. And then in terms of how the offshore wind industry and the wind energy industry more broadly is moving, talk about some of the challenges around manufacturing of wind turbines, some of the challenges around putting them out in the environment, because it's not that easy a place to do engineering type things in the middle of the North Sea. A bit about operational challenges and how that then leads on to the need for things like automation, robotics, smart systems. And I'll just talk through an example of some work that we're doing to try and make wind turbines a little bit smarter. And then I'll just touch on very briefly some of the skills that are involved or will be needed in the future. So, as I say, you're probably very familiar with this, but sometimes it's useful to remind ourselves of what the challenges are and why we're doing this. So the graph on the left is showing two things really: the growth in population, which we're very familiar with, and also the growth in energy use over the last 150, 170 years. And clearly, energy use is growing faster than the population, so the pro rata use of energy is increasing. As we become wealthier, more developed, we're each using more and more energy. And that's leading to more and more CO2 emissions. The graph on the right is showing how that's split between different regions. Actually, the Europe and the US, in a sense, are doing okay. They are reducing their carbon emissions, but places like China, India are still growing quite strongly, and the overall total is growing hugely. So you'll be familiar with some of this, but it's kind of good to remind ourselves from time to time. This shows the projections of what that might lead to. So the solid line at the left of this shows what we have been doing for the last 30 years. The projections going forward are what the options might look like depending on what we do from here on in. And essentially, starting at the top, if we didn't do any actions, hadn't done anything to reduce our carbon emissions, then we'd be looking at a 4 to 5 degree temperature rise. Fortunately, we are doing some things. So current policies, if they're maintained, would limit the temperature increase to around 3 degrees. If politicians and others fulfill what they say they'll do, then that brings it down to 2.5 to 3 degrees. But that's still a long way short of where we need to be, which is really the 1.5 degree pathway. So it's still a huge amount of work to do. And just in terms of what those temperatures mean, even 2 or 3 degrees, as we're already starting to see, is more forest fires, more droughts, more extreme weather. So the importance of addressing these, I think, is coming home to people, and policies are moving in the right direction, but there's still a long way to go. And policies only go so far. If you haven't got the technology to deliver on some of those things, the policies can't really achieve very much. So clearly, there's a demand for renewable energy, and there are options available to us. So just, I think I've not really thought about what does renewable mean. So I think quite a useful definition of renewable energy is a source that's replenished on human timescales. So things like solar are kind of instantaneous. Biofuels might take a year to grow something and replenish it. So that kind of is replenished on a human timescale. But if you think about coal, you're then talking about millions of years, and so it isn't replenished on a human timescale. So if you're looking for how to demark renewable and non-renewable energy sources, then I think that's quite a useful way of thinking about it. And these are the main options available. So wind, marine is wave and tidal, which I'll say a little bit about. Solar, we're familiar with. Hydro, we're very familiar with. Geothermal, extracting heat from the ground or maybe the air. And then various sorts of bioenergy. And all, I think, have their place in the future energy mix. But it's also important to think about what are the advantages and disadvantages of each of them in general and in the UK specifically, but also in terms of how much energy they can actually provide. And I think this is quite a useful illustration to understand that. So essentially, the size of these circles represents the amount of energy that's available. So if we captured all of the available energy, how much would that be? And the numbers shown, let me just get a pointer, 225 are illustrating how many times over that source of energy could fulfill the world's needs. So for instance, solar energy could provide all of the world's energy use 2,850 times over, which is great. It would mean covering the whole Earth with solar cells. So there's a limit to that. If you look at wind could provide 200 times the Earth's demand, biomass 20. But if you look at hydro, even if you exploited all of the hydro energy that is out there, we would still only meet the world's demand once over, and there would be no spare capacity there. So I think it's important to understand how much of these different sorts of energy there are, and one way of thinking about that is thinking about where the energy comes from. So apologies, this is rather a busy diagram, but what it's meant to be showing is where the ultimate source of energy is coming from, and what kind of transformations it has to go through to to be usable. And as it goes through each of those transitions, we lose a proportion of the available energy. So the more transitions it has to go through, the less energy there will be available at the end of that. So, for instance, the main source of energy for the Earth is the sun, and so if we directly convert the sun's energy through solar converters, then we get a lot of energy because it's a very direct process. If you looked at the wind, for instance, you require the sun to generate winds and the Earth's rotational energy to shape it, but that's quite a direct transition, and so we get quite a lot of energy in the wind. But if you look at hydro, what that has to do is you need the sun to evaporate moisture, you need the wind to transport it from over the sea to over the land, and those processes are quite inefficient. So by the time you've got water ready for your hydro system, it's got a very small proportion of the original energy that was put into it, and so it's not able to supply a large proportion of what's required. Similarly, waves and tidal, so as you'll be aware, tides are driven by the moon's motion and the sun, but those are quite small amounts of energy, and so the energy in the tides is relatively small, and waves driven by wind and tides are also relatively small amounts of energy. Moving back to the left, biomass is directly generated from solar energy, but that conversion is a very inefficient process. So only a fraction of 1% of the energy that's coming from the sun is actually converted into bioenergy. So that conversion is very inefficient. And then finally, geothermal. There's lots of energy stored in the Earth, but it's actually quite difficult to get out and to do that efficiently. So although there's lots of energy there, the conversion is quite inefficient. I'll say a little bit more about wind energy, and then look at how we do the conversions between comparison between different energy sources. So as you'll be aware, the Earth is driven, the wind is driven by the sun warming the atmosphere, and then that movement of air is shaped by the rotation of the sun, by the rotation of the Earth. So the Earth drags the atmosphere around with it, and so we get these quite complex patterns of winds around the Earth, and different regions obviously have different patterns of wind energy. That's also shaped by the local topology, the land surface, and particularly the roughness of the Earth affects how much wind energy is available. And it just so happens that the UK has some of the best wind resource in the world. So this map on the right-hand side essentially shows how much energy is available in different regions from the wind. And rather confusingly, red means there's not much energy at all. Yellow and green means there's lots of energy. And so the best places in Europe and actually in the world are in the North Sea, which is very convenient for us. It's also very convenient that the North Sea happens to be very shallow, and so it's relatively easy. I say relatively easy to exploit that resource. And I thought, as an engineer, I couldn't avoid putting one equation into a presentation. So this is an equation for the power that you can get from a wind turbine. And I only put this in because it's important to understand what are the key factors in getting as much energy from the wind as we can. So the power is a half. CP is just a measure of how efficient our turbine is. And so there's a limit to that. You can't get more than 59% of the available energy out of the wind. Rho is the density of the air. We can't do much about that. AT is the area of the rotor. So if we can make the rotor bigger, we get more power. If we double the radius, we get 4 times as much power. And then the key one is the wind speed, U cubed. So if we double the wind speed, we actually get 8 times as much power. So what we really want to do is have large turbines, big AT and high wind speeds. And so you'll probably be very aware of how the size of turbines has increased over the last few years to an incredible extent, actually. We now have turbines that are getting on for 10 times the size of what they were even 30 years ago. So that increases the area, but also making them taller increases the wind speed, because the wind speed increases as you go further up. But these are challenging things to make. The size of these current turbines are huge. They're some of the biggest structures ever constructed, and the pace of growth is incredible. In fact, this one is shown as future. These 10 megawatt machines are already being built, in the Siemens blade factory in Hull, in other turbine factories elsewhere, and we're already starting to move towards these 20 megawatt machines. So just going back to our comparison of different renewable energy sources, there's 2 factors here that are key in that comparison. So one of the issues is how much CO2 do you generate in the process of generating a certain amount of energy. So on the left, it's essentially showing how many tons of CO2 or equivalents do you have to generate for each kilowatt hour of energy that you produce. And so if you look, for instance, at the top, burning coal generates typically 1,000 grams of CO2 for every kilowatt hour that you generate. Similarly, for oil, natural gas, they all have relatively large amounts. Obviously, there's lots of talk about carbon capture and storage. So, you burn coal or gas, but you capture the CO2 that's emitted. One of the issues is that even the most efficient current processes are not that efficient. They don't capture all of the CO2. So although the CO2 emissions are a lot lower, they're only maybe 80% lower than if you burnt that fuel without the carbon capture. So even with carbon capture and storage, there's still relatively large CO2 emissions. Nuclear, as you would expect, is quite low. Biomass is not so low, because there's a lot of fuel used in transportation, fertilizers, and so on. Solar is quite a lot, because there's actually a lot of energy used in the manufacturing processes. Geothermal is relatively good. The best ones in terms of CO2 are onshore and offshore wind. Hydro is an interesting one, because obviously the rain falls, it flows through rivers. There's no obvious source of carbon there. The key thing there is that there's a huge amount of concrete used in the construction of a typical hydro system, and so there's lots of CO2 emitted in that manufacture of concrete. Obviously, we're also very aware of the price of electricity and the drive to reduce that cost. And so the graph on the right really just illustrates that the cost in pence per kilowatt hour of different types of energy. And again, I won't go through all of these in detail, because quite a few of them are similar. They're split in terms of construction, operations, fuel, disposal of CO2, if that's part of it, and the carbon price. So things like biomass, the actual kit for extracting biomass energy is relatively small, but you're paying a lot for the fuel and to transport it. And again, wind comes out pretty good, and actually these numbers have decreased again quite significantly. So this is a little bit out of date. For offshore wind, we're now talking about 4 pence per kilowatt hour. And I saw yesterday there's been an auction in Spain where onshore wind is now going to be 2 pence or 2 euro cents per kilowatt hour, which is a huge reduction in price. One other comparison, which I'll show, it's a little bit less appealing, is around the health and safety of these different renewable energy sources. And one measure of that is in the number of people who are killed in the process of generating that power. As I say, not a particularly nice thing to think about, but it is important in the overall picture. And again, some quite surprising comparisons. So if you look at those technologies, it's not obvious which are the safest and which have the biggest issues around health and safety. And if you look at the data, what it shows is that actually the worst is coal, because there are lots of people killed in coal mines, particularly in some areas of the world where health and safety rules are not so carefully applied. Similarly, oil is quite a dangerous industry. Nuclear, you might think, is a very dangerous industry, but because it is so dangerous, it's so well regulated that actually it is a very safe industry. Hydro in itself is relatively safe, but as we've seen a few times, unfortunately, when a dam fails, potentially there's a very large impact and potentially large numbers of deaths. Solar, the issue there is people falling off roofs while installing solar panels. Wind is relatively safe, and again, that's partly because it's quite a well-regulated, well-managed industry. What I would say is some of these figures are a little bit open to challenge. So, for instance, nuclear, there are direct deaths and then there are indirect deaths. So depending on who you talk to, the effects of the Chernobyl nuclear disaster were officially 3 people were killed in that, but obviously there are lots of people killed because of the radiation and the fallout from that. So these are open to some challenge. Okay, so hopefully that's kind of established that wind energy is one of the key things, and particularly in the UK is one of the key things. So moving to how that sector is developing, there are really 3 elements. One is that they're just getting bigger and bigger. So the rate of increase is incredible. So I work closely with the blade factory in Hull. When it was opened, I think 3 years ago, they were making 75-meter blades. They've since that had to knock the end walls out to extend it because they're making 83-meter blades, and now they're starting to look at 110-ish meter blades, and other manufacturers are doing the same. So these things are huge structures, very difficult to manufacture cost effectively, difficult to transport, difficult to generally deal with. So getting bigger, getting into more remote locations. So there's a number of drivers for that. So as you move further from shore, the wind becomes stronger and more consistent, and that's one of the things that you really need is strong and consistent wind. Also, as they get bigger, the visual impact becomes stronger, and so there's pressure to move them beyond line of sight. But that movement further from shore tends to mean that you're moving into deeper waters, and that introduces lots of challenges. And areas where they're more prone to extreme weather, and also it becomes more challenging to get people out to the turbines to do installation and repair jobs. And that's really just in the UK. In the UK, we've been very effective in exploiting the shallow areas of sea in the North Sea, but because of the pressure to increase capacity even further, we're going into deeper water around Scotland and further afield, and so it becomes more and more challenging to deal with that. But then also the industry is expanding worldwide. So in the US, there's a very strong push to develop offshore wind, and in Taiwan, Japan, and so on, areas which are more subject to extreme weather, storms, hurricanes, etc. And so you've got to be able to deal with those very extreme weathers. And because of that, because you're further from shore, in more extreme conditions, there's a lot more attraction for making the systems more autonomous and smarter, so that you don't have to send people out to do repairs. There's a saying in the industry that the most expensive part of a wind turbine is the door, because as soon as you open the door to get a technician inside, it's costing you about £10,000, because you have to stop the turbine to do it, you have to get someone there, you have to in fact have a team of people there, because you can't have people working on their own. So every time you open the door of a wind turbine, you can write off about £10,000. So if you can avoid that by making the systems more reliable, smarter, and doing more things autonomously, then there's a great deal of attraction for that. And obviously that needs new technologies. So just picking apart some of those, I'll talk about some of the manufacturing challenges first. And this is something where I've been doing quite a bit of work to try and improve the processes and understand some of the processes. And again, these things are huge. They're quite, in some ways, simple structures. They're essentially, wind turbine blades are made out of glass fibre, balsa wood, other wood. You know, it's not high-tech materials, although there is a move towards using more advanced materials. So typically what you have, just on the top right here, is some wooden elements to give it strength, some balsa wood to give it volume, and then a glass fibre shell that gives it the aerodynamic performance that you need. But that glass fibre isn't just the kind of thing that you would patch your car with. It's a very complex structure. So this is just an illustration of each of the layers of glass fibre has different characteristics, different strength, and different directions. And it's actually a very precise process of manufacturing and very carefully designed. But it is still a very manual process. So this is a half-built blade, but essentially the way it's made is the operatives lay down layers of glass fibre, one on top of another in a very defined sequence, smooth it out, because as soon as you have a wrinkle in that glass fibre, then it's an area of weakness, so it has to be very smooth. You lay up all the layers, close a mould, and then inject epoxy resin into it that then cures and makes the solid blade. So it's a mixture of quite a lot of manual processes and then some limited automation, but trying to improve that, make it more consistent, more automated is quite a big push within the industry. And then looking at the marine environment where we want to put these devices is a challenging and a complex place. So the figure on the right just illustrates some of the issues that a wind turbine has to deal with. So obviously there's wind, and we want to put these turbines in places where there is a lot of wind, and so we can't really be surprised that wind causes us problems. What would be nice is if we could get nice smooth wind that was flowing consistently all at the same speed. But what you actually get is you get different winds at different heights. So as you go up in the atmosphere, generally the wind speed increases, but it's not smooth, it's turbulent, it's mixed. And so you get this turbine gets buffeted by changing wind speeds. You get things like low-level jetting, where you get extreme winds at relatively low levels that then cause a big effect. You have things like ice, so these are operating in some quite cold atmospheres, and if you imagine a 100-meter long blade spinning around with large lumps of ice attached to it, that's obviously got a potential for a lot of danger associated with it. Lightning, if you're out in the sea, a 150-meter, 200-meter tall wind turbine is a great attractor for lightning, and potentially that lightning can do a lot of damage to a turbine. There's waves and tides affecting the tower. So this one shown is a floating wind turbine. Most of them are on towers that go straight into the seabed, but still the waves hitting the tower and occasional extreme waves cause a lot of problems. We have currents and tides flowing, and they put loads on the tower, but also tend to remove the soil. So if you imagine this is in a bed where there's soft sediments, the flow of tides and currents can remove that and makes the tower less strong. Fortunately, in the North Sea, that we don't get many earthquakes, but we do have other potential impacts. So there's things like unexploded ordnance on the seabed. There are other pieces of infrastructure. So it's quite a challenging environment to work in, and so making sure that wind turbines survive in that situation is quite a challenge. And just focusing on the North Sea there, so this is just an illustration of what's going on at the mouth of the Humber. There's a lot going on out there. So this map just shows wrecks. So the little ships are the various wrecks. The lines are pipelines to oil and gas installations, cables to other countries and so on. And so if you're wanting to put a wind farm in this environment, then there's a lot of things to take into account. There's also shipping lanes, I say unexploded ordnance, fishing rights. So it's not a case of you just pick a piece of seabed and you can start installing wind turbines. Also, the depth of the sea is quite variable, and so it's much easier to install turbines in shallow sea, but there's only a limited amount of space where there is that shallow sea. And we are talking about very large areas of seabed that we need to use. So you'll probably be aware of the Hornsey offshore wind development. If you take the 4 Hornsey offshore wind farms together, from west to east is the same distance as from Liverpool to Hull. They are huge areas of seabed that are being used for these installations. And installation and commissioning is not an easy thing. These are huge structures that have to be put into the sea, and there's lots of technology and infrastructure needed for that. So the picture on the top left is the Greenport Hull development, and it is incredible the way these things are now done. So these 2 what are called jack-up vessels are essentially huge boats that will load up with a kit of 4 wind turbines in Hull. So you'll see there's 4 towers, there's 12 sets of blades, and there's 4 what are called nacelles, where the generator and the control gear is put in. So they load up in Hull, they sail out, for instance, to the Hornsey development. They jack up on their legs, so they put the legs on the seabed so they're raised above the sea and have a stable platform, and then install those kits of parts. And essentially what Siemens were able to do was what they call 24/199. So within 24 hours, they can install a complete wind turbine, and 99% of the time it will be working and generating power within that one day, which is an amazing achievement given the challenge in that environment. But it's also necessary because, for instance, again, Hornsey 1 had, I think, 174 turbines in it. And if you take 2 days to install it rather than 1, you're talking about huge amounts of time that implies. Just by way of contrast, the installing offshore has some issues, but it also avoids some issues. If you're looking at onshore turbines, there are lots of challenges around transportation, installation. So, just as an example, this is a blade being transported by road. If you imagine, you might be able to do this once, but if you're wanting to do this, three blades per turbine, maybe 100 turbines per development. If you're living around here, you're going to get pretty fed up of these wind turbine blades going past your house and blocking up the roads every day. And onshore, typically you're installing on the tops of mountains, and so you've got to try and get these huge structures up winding mountain roads. So although offshore has its challenges. Onshore has some bigger challenges in some ways. Another issue is around access to turbines. So although we try and reduce the amount of time people spend on turbines, it does have to happen. There has been huge progress in improving that. So it used to be that typically you would have to spend a week on a turbine getting it commissioned and then visit it several times in the following months to iron out little problems. Now, typically once it's installed, as I say, in one day, you're then talking it may not be visited for another 6 months, but you do still need to. And traditionally, the way that's been done is with what's called a crew transfer vessel, or what's some people refer to as bump and jump, where the vessel essentially sails up to the turbine and then the technicians have to jump across. And I'll just play this video to illustrate what that looks like. A look of relief on his face. So clearly the vessel moved lots, a lot of potential during I should say even the state itself jumping. Essentially, the guy on the boat is looking for when the waves are looking smoother, and then so not something I would want to do. So alternatives are helicopters, but obviously expensive and not without some risks. And now increasingly what they're using is these crew transfer vessels, which are much bigger, much more stable, and have a thing called a walk-to-work system, where there's a motion compensated gangway. So essentially the vessel may continue to move, but the gangway stays still, and so you can just walk across that to get access to the turbine. But all expensive and potentially prone to dangers. So what we would like to do is avoid that and try and make the system smarter and more autonomous. And so even now, turbines have lots of sensors to measure all kinds of things. So temperatures in gearboxes, electrical quantities, gearbox condition, and movement of the tower, movement of the blades, and so on. And they generate literally gigabytes of data. So the amounts of data that these generate is huge. And one of the problems is that there's so much data that in lots of cases, no one really knows what to do with it all. They're all connected together. So a whole wind farm will be connected together with fibre optics that then feed into a control room. So some of you may be aware of the East Coast hub for Ørsted in Grimsby, where all of their East Coast turbines are monitored and checked. And essentially what they're trying to do is three things. They're trying to detect if something's gone wrong. So maybe if there's a problem in a gearbox, they may just initially say, okay, there's a problem with this. Then they're trying to work out what is the problem. So it's a damage to a tooth in a gearbox, so they know what it is and maybe where in the system it is. But then also importantly, how quickly is that going to deteriorate, and at what point do they need to do something about it? Because as we've seen, getting access to these turbines is a challenge. You want to be able to plan it so you use the best weather window that you can, and so understanding, is this something I need to fix today, or can I leave it for a couple of weeks, is an important consideration. But that needs smart sensors, and some of the quantities that we want to measure aren't that easy to measure. So some of the work we've been doing is looking at putting smarter sensors into wind turbine blades. And that's important. So the blades of a wind turbine have a pretty hard time. The tips typically travel at about 200 kilometers an hour, and they'll rotate around 50 million times in a lifetime. So there's a lot of fatigue, lots of opportunities for damage. And what you want to do is know that there's a problem before you get to the state where that turbine on the right-hand side has reached. That potentially, if a blade breaks like that, it can hit the tower and the whole turbine can be destroyed. If you know that it's approaching the end of its life, then you can plan some action to either repair or replace it. And so what we're looking at is using fibre optic sensors to do that. So just very quickly illustrate how that works. Essentially, a fibre optic is a tube essentially carrying light down it. And what we can do is change the internal structure of that by putting in what's called a grating. So it's like a filter that allows some light through and reflects other light. So if we pass a spectrum of light down that fibre optic, then the way we've made that grating will cause some of the light to be reflected, in this case the green light, and then the rest of the spectrum will pass through it. And what we can do is look at the shape of that light to work out what's going on in that grating. And if we stretch that piece of glass fibre, it will change the shape of that and it will change the reflected light. And so monitoring that change in the wavelength of light coming back allows us to monitor the strain that is applied in that fibre optic. And so what we're looking at is putting multiple sensors in, a whole network of sensors. So we'll get a whole load of these peaks in the spectrum, but it will tell us what's the strain at this point here, or this point here, or this point here. And from that, we can deduce how much fatigue that wind turbine has been subject to and whether it's starting to be damaged and deteriorating. But more widely, there are things that we can detect with sensors, but there are also things that we can't very easily detect. And so again, having autonomous systems for inspection and repair is an important area in the industry. So, as I said before, these wind turbine blades are typically doing 200 kilometers an hour, passing through rain, hail, snow, salt, and so you get a lot of damage to the front of the blade. If you imagine driving your car at 200 kilometers an hour for, I think it's about 3 million miles or 3 million kilometers, you'd expect to get quite a bit of damage at the front of your bonnet, and that's what you get in these blades. And that has a big impact on the amount of energy that you extract. So it would be, there's a lot of pressure to inspect and potentially repair these kind of blades. And conventionally, what it involves is a technician sliding down a rope, inspecting the front of the blade, and then using filler and a sander to replace that. Not a job that would appeal to everyone, and although it looks quite pleasant on a sunny day like that in the photo, it's not so easy when the wind's blowing and the rain's falling. So already there's a lot of work around using drones to do the inspection. So having drones flying up and down the blades, doing the inspection, automating the analysis process, and then moving towards robots that can then crawl along a blade and carry out the repair. There are lots of other repairs that need doing, and some of them, are much more challenging for autonomous systems because of the size and weight of the structures that you're talking about. Replacing a blade would require such a huge autonomous system that it's probably not practical, but some of the other inspection and repair processes are possible. And then there are things like surveying the seabed, transporting parts and tools that are starting to be developed. So that's the kind of current state and where things are moving to. But there's, we're only really just beginning. So this is an image from the recent white paper around energy, showing that the role of renewables is probably going to be increased by a factor of about 4 over the next 30 years. In the case of offshore wind, it's expected to increase fourfold within the next 10 years. So going from 10 gigawatts to about 40 gigawatts and then to 75 gigawatts. So huge opportunities there and huge need for skills. Also energy storage, because obviously the wind is intermittent, solar energy is intermittent, so energy storage and management of the demand so that you can try and match demand to when the energy is available will be important. So just to wrap up, that has a big implication in terms of the future skills that will be required. And it's conventionally, when people talk about skills in offshore wind, people tend to think of people who are technicians who will shimmy up and down wind turbine blades, or engineers who design blades. But actually there are a huge range of other skills that are involved. So as hopefully you've seen, there's lots of work in terms of IT and data science, understanding all those gigabytes of data and interpreting them, understanding the environment, both in terms of how is the wind affected, but also how does the offshore wind installation affect the environment that it's operating in. So things like movement of the seabed, noise, how are those affecting the animal life? Lots of challenges around manufacturing and materials, but also project management and planning and so on. Just as an illustration, this photo is a group of master's level degree apprentices who we've been working with Siemens Gamesa to develop. So essentially Siemens Gamesa recruited a group of apprentices. They've been studying here at the university and then doing placements in various parts of the company. And it's really been good in terms of them developing the academic knowledge, but also being able to apply it to their day-to-day jobs. And so we're working with them for another cohort of those students at the moment. So hopefully that's given you a picture of the kinds of things that we're doing on, some of the opportunities and some of the challenges that there are around renewables generally, and particularly offshore wind. So thank you for your attention. I'm very happy to take any questions or comments on that.
Paul. I didn't know if somebody was going to say, Paul, go ahead. So I'll just ask anyway.
Yeah.
Thanks, James. It's a wonderful presentation, actually. I got an idea that gearboxes were going to be sort of phased out because they're the things most likely to break down. So I'm sure I'd seen that there were designs coming up that didn't have gearboxes. Can you comment, please?
Yes, you're absolutely right. One of the biggest causes of loss of production is gearboxes. Not that they fail particularly often, but when they do, they're very difficult to replace because they're in the heart of the machine. You need very special vessels to do that. So yes, the current trend is towards what are called direct drive gearboxes. So all of the Siemens offshore wind turbines are direct drive, and actually we work with Sheffield University, who've been very involved in the design of those. There are implications that it impacts on the design of the turbine. It impacts on the use of materials. So those direct drive generators need rare earth materials, which the name implies they're not very common, and so there's issues around that. And interestingly, there's a development in Hull planned around rare earth magnet manufacture for offshore wind and electric vehicles. So yeah.
Thank you.
Steve, do you want to go next? Sorry, I'll get people out of sequence.
Yes, thank you very much, James. Yes, thank you. Very good presentation there. Particularly towards the end, you focused on skills, master's level apprenticeships that you're running at the moment. I'm working with Bradford College on the Future Technology Centre at present, and what we're looking to do is looking at skills development in the whole range of areas that you specified. But I was wondering if you'd done any work in identifying at what level we would be looking at in terms of skills demand, let's say over the next 5 years. Is it level 1 through to, what numbers from level 1, let's say, through to level 7?
Okay, so I can partially answer that. So a couple of years ago, we did a study, or we commissioned EU Skills to do a study of projecting the need for skills in offshore wind up to 2030, I think it was, and broke it down by kind of technology area, region. It did look at different levels. I'm not sure how granular that was, whether it was so many at level 1, but certainly there's an indication of the kinds of levels of different roles. So I guess once we've finished, I can put a link to that report on the team's site. And then we're also, one of my colleagues is working with I can't remember what it's called, the Green Skills Working Group or something, to look at future needs. So if there's continuing work going on that, and certainly we'd be happy to talk through what we know, which I wouldn't claim that we know anything, but everything by any means, but we have done some work in that area.
Great. Okay, thank you.
Rachel, would you like to?
Yes, thanks, James. Again, great presentation. So thank you for that. And I will put my camera on as well. So sorry. So I was just wondering, when you're locating the wind turbine areas, are bird flight paths and feeding habitats considered in that, and are they going to become more important in the future? Because there's been a few things on the news with damages to different bird populations.
So the short answer is yes, it is a very important consideration, because yes, there are dangers of impacts, and understanding how the presence of a wind turbine affects bird flight paths is quite complicated, because there's different things that happen. Some species will fly through a wind farm, others will fly around it, others will just move to a different area, and obviously as wind farms get bigger, there's more potential impact, and as part of the planning process, you have to prove that the impact will be manageable. So there was a recent, you may have seen that Hornsey 4, I think, recently got approval in spite of some issues around the impacts on birds. And so Ørsted, who are doing that development, will be obliged to mitigate that by supporting wetland development and other things to support the populations. One of the things that came out of that, and I can't remember the exact details, but it was, I think the figure was that over the lifetime of the wind farm, there would be around 86 collisions between a bird and a wind turbine, which is obviously a lot, but compared to, and I can't remember what the comparison was, it might have been power lines, conventional pylon power lines were hugely bigger numbers. So although it is an impact, it compared to some of the other factors, it was a relatively small impact. And of course, the impact of climate change potentially is hugely more significant. So it is a consideration, and people are doing research on it to try and discourage birds from impacting. And there is a study that says that if you paint one of the 3 blades black, then birds avoid it more than if they're 3 white blades. So no one really knows why, and I don't know why they kind of did that study, but yeah, it is a concern to the industry. And there are other environmental impacts, so the noise generated during construction can affect fish and mammals and so on. So we've actually got what's called a Centre for Doctoral Training. So we have funding for 75 PhDs looking at offshore wind and the environment and how those interact with each other. And so there's a couple of PhDs looking at impacts of noise on mammals and other sea creatures. So it is an important area of work.
Right, I guess in the future, the height, as you said, they were getting bigger and higher. So that's going to be another differential, isn't it, to understand in terms of flight paths. I suppose the black blade would differentiate it between clouds, and depending on their visual aspect and how they fly through, it just makes it a difference, which is great. But thank you.
Yeah, no problem. Thank you. Okay. Well, if there's no further questions or comments, and I'll thank you very much for your attention. Thanks for your questions, and if there are any other questions that come up, then please let me know, and I'll put that link to the skills report onto the team site once I've got access to that.
Thanks very much, James. That's really fascinating and really interesting to see all the challenges that are involved, actually, with a lot of things you kind of take for granted now with seeing wind turbines. So yeah, really interesting. And yeah, we'll make available the link to the report on the Teams for those that have access to that. So thank you.
Okay, thank you very much.
Thank you, everyone.
Thank you. That's great.
Thank you. Thank you very much.
Hi, James.
Yes.
I'm sorry. My name's Nick Drury. I'm from Bishop Burton. I didn't want to sound dumb with all those people there and ask this question, because I'm not an engineer. I'm not technically minded. But you talked about height and the width of the blades.
Yeah.
Is there a big difference? And is it not possible to heighten the pole that the blades are centered off, rather than actually increase the length of the blade? Don't know why.
So there is. So basically, what happens is as you move higher and higher up, the wind speed starts off low and then gradually increases. So if you go from, say, 50 meters to 150 meters, the wind speed, depending on the ground cover, may be 50% higher. So you get higher wind speed, and so you do get more power. But you get a bigger effect from a bigger rotor. If you make the rotor twice the diameter, you'll get, as I say, 4 times the power. If you increase the height, if you double the height, you may only get 10% more power. And so there's a combination of the two. They are taller, but you do need that bigger rotor. Also, if you just make them taller, then you imagine you've got a much longer lever, so it becomes much more difficult to keep them solid. So you end up using more material in the tower. You have stronger foundations, and so you're increasing the cost.
Yeah. I was just curious. Thank you for that.
No problem. No, very valid question.
It was very interesting. Thank you very much.
Cheers.
Cheers. Bye bye now.